What we'll be covering, orbital debris. NASA just came out with a new study on what they think is going to be cost effective for getting rid of some of the orbital debris. That's what this picture is representing here. You've seen these kind of graphs before showing total number of objects in space is going up and up and up. In fact, even the ones that are actual spacecraft, the blue line on this graph, you see they're really shooting up. And it's just because there's all these constellations of satellites going up. Starlink, OneWeb. The Chinese are going to put up 3,000 satellites pretty soon. Everybody's just throwing lots and lots of satellites up there. The number of rocket bodies isn't going up as fast. What happens typically, the first stages always fall back to Earth, either uncontrolled or controlled, but one way or another they go back. But the second stages and higher typically get stuck up there. And so they just start tumbling around. But we're packing more and more satellites into each rocket, so the number of objects is going up faster. But then the big problem is the debris. That's the dashed purple line here. And there were some big jumps, like, for instance, there was a Russian anti-satellite test that did one of these jumps. There was another one, was a Chinese one, and there was one where there was just a collision between a Russian satellite and an Iridium communication satellite. So every time you get a collision, you get extra debris up there, and it's just building up and building up. So, that's been a concern, and so people are wondering, what can we do about it? Well, they studied this, and they looked at the problems. They tried to put it in terms of actual cost instead of just doing it as a moral issue. So they said, if you have debris up there, you have to maneuver around it. That costs you propellant. That also costs you analyst time, even to figure out what to do. People have to make decisions on this kind of stuff. But then, of course, you're actually talking about the safety of astronauts, but also the safety for the other craft that are up there. As I said, there was a crash between an Iridium satellite and some other stuff. It does happen, and then there's an economic loss there. Now that, of course, you have to weight by probability. So the whole thing is based on expected value. You say, okay, it might cost you, $10 million, but it's maybe a low probability. We just multiply that probability to come up with something, get an idea for, what the cost might be. So what are the methods for reducing debris?
One other thing is that this is a real problem because they didn't think there was a very high probability of this debris being significant. And then twice in like the last 4 months, the Russian spaceships have gotten holes in them, spitting out fuel or some kind of liquid into space.
Yeah. Now, of course, they're saying it was just a micrometeorite. I mean, there are always things up there doing it. And of course, they're not going to ever admit that it was one of their own anti-satellite tests that did it. And we will probably never know. Well, they were trying to blame American astronauts for using ice picks or something, too. I mean, there was just, all kinds of crazy stuff there. Blame everybody but yourself. That's the general rule. Okay, so anyway, reducing the risk associated with debris, there's really 3 ways to attack it. The first one is simply don't create it in the first place. So for instance, there are protocols. The standard really is to make sure that if you have a first stage that goes really high or even a second stage, make sure you can actually deorbit it. Or if you have a satellite up there, make sure you have a plan for deorbiting it at the end. And there's various ways of doing that. We talked about some last time. Dropping a tether, which increases air resistance and in particular interacts with the Earth's magnetic field, slows the thing down. There's lots and lots of ways to do that, and it's being done, actually. So that's one way, and that's been attacked at least. The second thing is simply to improve the tracking and characterization. And then at least you can do more collision avoidance, because sometimes people just get blindsided. They don't even know it's coming, and then it hits them. And maybe the space station is an example of that. But then the third approach would be to remediate the debris, basically try to go around and collect it one way or another. You need a garbage truck up there to pick this stuff up. And so that's really what the focus of this study was. So it was remediation, not avoiding it, but remediation. They just said, okay, let's just do a couple of scenarios. Look at large debris, meaning more than 10 centimeters. People before have identified what are the 50 that are the most concerning pieces of junk that are up there that people are worried about. And say, okay, we'll just do a case with that and see what it takes to remove those. And then for small debris, that is between the 1 to 10 centimeter size, they said, okay, what if we removed 100,000 pieces of that? Because a lot of these objects that I was talking about in that graph up there, I don't think they don't even go down to 1 centimeter. There's a lot of really small stuff up there. By the way, these scenarios did not include the worst cases, the Kessler cascade kind of thing, where something happens and it makes some debris, and then that debris hits more things, and the whole thing kind of builds up. They didn't actually think that was that likely yet. They factored in one additional level. If 2 pieces of debris collided, that it would generate some more, but the probabilities dropped off. They didn't see that coming right away. But what are the benefits for it? We talked about the satellite operators. They actually have to use their propellant in their satellites to move around, if they can. Not all satellites can maneuver, but most of them have some maneuvering capability. Surprisingly, that really is very few dollars per year, $58 million a year, which is really not that much. A lot of people were surprised at that, including the guy who runs OneWeb, which is the next biggest competitor right now to Starlink. They have maybe 600 satellites up there, and they're just starting their internet service now. He says they actually get 53,000 warnings a day from the Space Force. Now, those things must be covering some pretty big distances, but they act on 6 to 8. They actually take maneuvers 6 to 8 times a day, they're saying. Now, that sounds 600 satellites or whatever it is. So still, that gives you an idea, though, they're doing a lot of this. What is the cost of that maneuvering? And one thing that I thought was kind of odd about this study was they decided that, well, while you're maneuvering, you probably are not able to use your satellites for the intended purpose. Like, you're probably going to interfere with communications and so on. So they said, okay, there's a cost for that. You're going to lose some revenue if it's a commercial satellite, or if it's a military satellite, you're losing the ability to monitor some war somewhere. So they counted that, but they didn't count for the fact that if you use up your propellant faster, ultimately the satellite can't stay up there as long. You've got to deorbit it because it's about to run out of fuel. And normally you save some fuel at the end for deorbiting. They didn't count for that. And that strikes me as a much bigger dollar cost. You might lose a year. If you lost a year out of a 15-year life at satellite, that's pretty significant. So anyway, it didn't look to me like they actually accounted for that, but they tried. They made an attempt to cover a lot of things. I think they just might have missed a few. Yeah.
We have a question from the online cohort.
Yeah.
Please explain why OneWeb will give Space Force warnings.
General service. It's true the United States probably does kind of assume a lot of responsibility because there aren't many countries that can actually track all this debris. And we probably are the most transparent about it, but somebody has to, so we've been doing it. We do it because we want to defend our own satellites. We have the most at stake by far, so I think it's probably our own self-interest. We have the most to lose from collisions, so we probably better do our best to prevent them. But that's my guess. Okay, so they studied a whole bunch of methods, and I'll actually give some examples of what these look like. But they said there's several approaches that might work the best. For small debris, they actually want to, what they quote, nudge, basically the small pieces of small debris with lasers, either based in space or on the ground. And we'll talk about that in a minute, because it's probably not what you're thinking. They claim that would be a 10 years investment. You'd get back your money in 10 years on that one. To me, it seems to me that there's probably a lot of R&D involved in this, because you're talking about hitting pretty small pieces of stuff pretty high up. They're moving pretty fast. It's pretty high up. Now, the thing is, this goes back to the 1980s military, Strategic Defense Initiative, or Star Wars, as they called it back then. They did a lot of research on using lasers and other things, for clearing out stuff in space back then. And a lot of this research really goes back to that period of time. You wonder how much of that is classified and can be used or not used. It wasn't clear, and they really glossed over that in this report, I thought. The other thing about using lasers, though, is that would trigger concern from everybody about their use as weapons. Anything that can take out a piece of debris can take out a satellite. It becomes a weapon of war. The claim was that the lasers they're talking about would not really be powerful enough to really do any serious damage to a normal operating satellite. Seems a little questionable, but anyway, that's the claim. And they had some study to kind of back that up. That's handling small debris. For the large debris, they said the best thing right now is pretty much just doing collision avoidance. And you do that by nudging the debris, again, with lasers or using small rockets, one way or the other. So you don't necessarily get rid of it and deorbit it, but at least you knock it out of the way, one way or the other. And they're saying 10 to 20 year break even for that. So what does this stuff look like? Ground-based laser. I mean, this does seem like Star Wars all over again, but you got some piece of debris going over here, and it's going from right to left across this screen. The initial orbit. And what you do is you zap it. But the thing is, you're not just vaporizing it, which is what you're probably thinking, because that's what it looks like. Actually, it's more obvious in a space-based laser case. Essentially, you're doing the same thing. You're just doing it from a satellite. If the debris is heading from right to left in this picture, if you zap with a laser in a very, very tiny little area, it'll ablate it, meaning it'll blow off pieces of it. And it's all going to be directed in the opposite direction of the orbit. That generates enough momentum that it slows the thing down. And eventually, as you see back in the previous one, they show that it'll take it to a lower orbit. You get it down low enough, and air friction will take care of it. You don't really have to get it all the way to the ground. You just have to get it low enough for air friction to become significant.
I imagine a lot of this material is spinning. How does that affect?
Well, that's actually one reason in particular that they favor the laser approach, because what they do is they use a pulsed laser where it's extremely intense for a very short period of time, and so it isn't going to spin that much during the period it's hitting it. In the mechanical means, if you're talking about collecting a big garbage can one way or another, it's kind of hard to grapple when it's spinning very fast. So that's actually one of the reasons why they like the laser. The key thing is that you deliver a lot of energy in a very, very short time.
Yes, the DOE does have nanosecond and picosecond lasers
Yeah.
already.
Some other approaches that you might think of, they say would really cost a lot more. Space tugs are the obvious one. You go out and you capture the stuff one way or another. The difficulties are, as you brought up, spinning. If they're spinning, it's just very hard to grab a hold of something. That's a lot of angular momentum. You're going to pick that up. So if you're up there, all of a sudden you're going to start spinning with it too. It's just hard to deal with. And it actually ends up just being a pretty expensive way to go anyway. But there is something related called a sweeper spacecraft, where pretty much just put up a big panel of very thick, strong cloth like Kevlar or something. It's shown in this thing here, where basically you just stake out an area and you just go through it with this big hunk of cloth. And you don't actually try to catch it, you just try to slow it down. It'll probably just penetrate, go all the way through it, but it'll slow it down enough. And again, eventually it'll get low enough, the air friction will take over and it'll go out of the atmosphere. And they said that should work, but it'll take 20 to 25 years to get back a return on that. Part of the problem is space is big. You can make this thing pretty big, but you're not going to hit very many of them. If you're just kind of up there just doing a general sweep, it's pretty hard. So unless you have a very specific area where you know there's a lot of debris, it's going to take a long time. With the lasers, they're basically just saying, watch, just wait and watch. You pretty much scan one area of sky. When you see something, you immediately zap it. And that's what I was saying. That also will take a lot of time, but at least it's you probably can cover more ground that way, or more space that way.
So this is basically like a big Swiffer in orbit.
Yeah, pretty much.
Or a catcher's mitt.
Well, it's a bad catcher's mitt because it lets the baseball right through, but at least it slows it down enough. Yeah, yeah. Now the other one is a little more exotic, or a lot more exotic. That they say actually is sort of promising, but it's going to take a lot more R&D, and that's recycle the metals. They've been funding through SBIR's Innovative Research Small Grants, orbiting foundries, where the idea is you repurpose the metal. This is more of a grappling kind of thing, but once you do that, you just melt it all down, very, very hot. And what's interesting is that they say they can actually make propellant out of that. There's a type of rocket engine called metallic plasma propulsion, where essentially you heat up just the tip of the metal and it goes shooting out, and actually aluminum works just fine as a propellant. Or alloys. Typically what's up there is going to have a lot of aluminum and have some other stuff. You're actually able to use that as a propellant. Anything that you can shoot out, you get a reaction from it.
Molecular, right? It's not really particles.
No, they're actually talking about doing a wire. They'll have a wire and they just burn the ends of it.
Right. When they burn the ends of it, what's emitting is not a particle. It's almost a molecule.
Yeah. Well, actually, it's actually plasma. So that's actually not really a particle. It's another state. I'm
just thinking about you might be creating the exhaust from that engine might be a problem after a while.
Well, apparently they don't think so. Apparently, whatever coalesces after that, from when plasma coalesces back to something else, it must be such fine particles that nobody ever notices it again. That's the principle. So in a theory, you could have kind of a circular economy in space where you got all this junk up there. You go and you find one. And by the way, there's all these companies that are working on kind of a project on this thing. Astroscale has been working on capturing small satellites. NanoRacks has worked on cutting them up, using robotic arms and lasers to cut them up or weld things together if they need to, but basically cut them in small chunks. Cislunar Industries has a technology for basically melting it and generating the wires. So they're all kind of working together on this as a project. Okay, now the trouble with recycling is the same problem we talked about with asteroid mining, that actually we're getting better and better at lowering the cost of getting up to space. So if you want to manufacture stuff in space, like wire rods, well, you're competing against ground-based wire rod production, and the cost keeps coming down. This is a slide just showing how costs have been coming down. We've had various slides like this before. I just hadn't seen this particular one before, where actually the shuttle was like $60,000 a kilogram to get stuff up there. And they got better over time, but still, it took, until you got down to the Falcon 9 here, that was already a factor of 10 cheaper. And actually, Falcon Heavy is even cheaper than that. And the next one didn't quite show up here, but, the next one, when you get Starship, it could be another factor of 10 or more. It's going to get that much cheaper. So actually, if you're going to try to make money by reselling stuff in space, in a way, it's almost unfortunate that we're going to have such cheap access. I'll take that trade. That seems worth it.
This is something log scale.
It's a log scale. So this is not linear. So we're talking, there's $60,000 up at the top. We're talking down here in the below $1,000. So yeah. Okay. So this is their summary slide, pretty much showing the benefit analysis. And what they do is they're plotting plot it as a year. How many years would it take to get your investment back? When you've assigned a monetary value to all this stuff. And so they show that for the small debris, which is the left-hand side of this picture, the ground or space-based laser were cheapest. The sweeper was a whole lot more expensive. For the large objects, they split it out into controlled and uncontrolled reentry. Controlled reentry means you actually direct it to a specific spot, usually the Pacific Ocean somewhere. Under uncontrolled reentry just means you get it low enough and eventually it slows down and falls down somewhere. If it's a small object, at least it'll vaporize before it hits anybody. Now they're saying the laser or the rocket, JCA is just-in-time collision avoidance. That means you just basically do a lot of diversions. They're showing a wide range here. The problem is they seem to be assuming that technology exists already, and I'm not quite sure that's true. But it varies a lot. I mean, if you have an opportunity, yeah, you would take it. It's hard to say. I don't know how they came up with the variation here, but these bars indicate a variation in a number of years it takes to get your money back. And the recycling option, they just said, well, there's a lot of R&D involved in this, so it's going to take a lot of years to get your money back. And that's the best they could do. Okay, now, of course, there's a huge debris problem coming up, actually, in a few more years, 2031. The end of life for the space station is going to be 2030. And what NASA is saying is they want to come up with some kind of solution for getting rid of this. And they say they probably would deorbit it in 2031. Maybe you launch craft up there to help propel it. They have a whole separate request that's gone out for proposals from industry on what do they do with this at the end of its life. It's a huge debris issue. And actually, all the techniques we talked about, some of them may well apply here as well as just having a giant garage sale, selling off the solar arrays and everything else. I'll talk about that next time, just to keep time down. I decided not to cover that this time, but this is the big one. It is coming up here. All right, any other discussion or questions?